Hello, everyone. My name is Hannah Turner, and I'm the president of the Marshall University Astronomy Club, MUAC. I thank you all for joining us for our Fall 2024 Virtual Speaker Series. Drawing inspiration from our sister organization, the Society of Physics Students, SPS, which utilizes their series to spread science knowledge to the public, MUAC has created this series with the intent of capturing a glimpse into the minds of astronomers from our surrounding communities. A fundamental goal of MUAC has been and always will be to encourage astronomy discussions among upcoming generations. When we provide a platform for such knowledge to flourish, we aid a sense of possibility to all children within our local communities. Becoming an astronaut, an astrophysicist, or even a leader of a university astronomy group doesn't seem so impossible. I speak for all leading MUAC members when I say that we are very proud of what we have accomplished with this club. With that being said, I would like to introduce MUSC advisor, Dr. Sean McBride.
Thank you, Hannah. I am an associate professor in the Department of Mathematics and Physics here at Marshall University. I want to really first thank Hannah for the excellent job that she's done with this speaker series. She has done an amazing job of going out and contacting professors and making all the connections, setting up the live stream. So she has done a phenomenal job, and I just want to thank Hannah for all of her hard work for the entire speaker series. The Astronomy Club is tied to Mathematics and Physics Department through me as their advisor. Our department here is a vibrant community of scholars who are passionate about exploring the fascinating intersection between mathematics and physics. In our mathematics program here, we have and physics, we have over 20 faculty members in that program. 8 of those are faculty members that are in physics. We have undergraduate programs in mathematics, physics, and statistics. We have graduate programs in mathematics, physical and applied sciences, as well as a concentration in pure physics. Marshall is sometimes described as just the right size university. We have about 8,300 undergraduate students and about 2,400 graduate students. There's about 550 students in professional programs, so MD, PharmD, DPT. 80%, 86% of the faculty hold terminal degrees in their field. If you have any questions about programs at Marshall in the mathematics or physics or any other field, even outside the College of Science, let somebody know, talk to an advisor. If you have any questions about what you hear tonight, please contact our speaker. Please contact me if you have any questions about Marshall or if you're interested in the astronomy club here. My email is fairly easy. It's mcbrides@marshall.edu. So just reach out to one of us if you have any questions, and we will be sure to get you on the right path for answering your questions. So with that, I'd like to turn it over to Hannah, and she will properly introduce our speaker.
Very well said. Thank you, Dr. McBride. So without further ado, it is my utmost pleasure to introduce our first speaker in this series, Dr. Duncan Lorimer, who will be speaking to us this evening on the cosmic mystery and history of fast radio burst. This talk will span 45 minutes approximately, followed by a 15-minute Q&A period for all listeners to send questions within our live chat. We do ask that everyone hold their questions until the end. Dr. Lorimer.
Thank you very much, Hannah. Really, I'm so glad to be here and to also be the inaugural speaker in this series. I'm coming to you tonight from Morgantown, West Virginia, home of the WVU Mountaineers, and I have been a faculty member at the Department of Physics and Astronomy here on the Morgantown campus for about 18 years, something like that. I'm going into my 19th year. And what brought me to West Virginia was the Green Bank Telescope and just the rich history of radio astronomy that is in this state, primarily at the Green Bank Observatory. And we've had a lot of fun over the years working with colleagues there and across the state as well on various astronomy projects. I'm going to tell you about one of those tonight, fast radio bursts, and they are a population of really as yet fully understood objects from across the cosmos, which we here in West Virginia, but also worldwide, there's a community of several hundred people that are actively researching. But it all started here in West Virginia, as I'll tell you tonight. just a quick orientation where I'm coming from here in Morgantown. This is a picture of the folks in our department recently. We are a fairly large physics and astronomy department. There's about 80 graduate students and about 60 or 70 undergrads, 25 faculty that work in a variety of areas, including astrophysics. So if you're ever in the Morgantown area, do let me know. We'd love to have you stop by our building here in Whitehall on the top of High Street. The things we do, in addition to astronomy and astrophysics, we get into really the study of the physics of materials, and particularly the physics of interfaces between materials, and our colleagues in condensed matter physics have a world-renowned program, both in experiment and theory in that. We have a number of experts in optical and laser physics, as well as a very vibrant physics education research program. Our plasma physics program is also excellent. We have a lot of experiments, state-of-the-art experiments and theory that's going on here. Some of our recent faculty accomplishments include a revision of the first law of thermodynamics from a space physics perspective. So there's a lot going on here. We do a bit of biophysics as well. So I'm going to be talking about radio astronomy tonight. And we're all fairly familiar here in West Virginia. We have, a beautiful state. We can go out, get away from the city lights and look at the sky with our unaided eyes, and we see the band of the Milky Way. And mostly what we're looking at there are stars in the Milky Way galaxy itself. When you look at the radio sky, and now if I'm looking at radio waves that are about 5 centimeter in wavelength, I see a completely different picture. So this is the horizon at the Green Bank Observatory in Pocahontas County here in West Virginia. But then on what you're looking at in the sky is now a radio map on that scale that you're looking at. So tens of degrees on the sky. And you see lots of points of light. You might think those are stars, but in fact, pretty much all of those little points of light are very distant galaxies. So it's a very different picture than we see in the optical. We also see extended radio objects. These shells at various points on the image many of them are in our own galaxy. They're expanding shells of gas from supernova explosions. And those supernova explosions produce pulsars, which we'll talk a little bit about tonight. What I'm going to play for you next, and hopefully the audio will work, is just a short clip of how the radio sky sounds like. And that will introduce these fast radio bursts to you. It'll give you an idea of the radio noise, sort of the background hiss in our electronics, and also the signals themselves. So I want you just to listen to this for about a 10-second clip. Okay, so hopefully you could hear that background rumble. That was noise from the sky, just a general radio noise from like a hiss, as you would get if you tuned your radio around, but also noise in our electronics as well. But what was really interesting that you heard there were the signals, these fast radio bursts, and you could hear them as chirps. They were converted into audio so that we could hear them, but the highest frequency is coming first, and the lowest frequency is coming later. That's a very important characteristic of the signal. The other thing that simulation was really giving you a sense of is the fact that these objects are coming very frequently. Once every few seconds, one goes off somewhere over the sky. So it's a real puzzle that we're talking about tonight. Okay, so let's look at one of these fast radio bursts. And what you're looking at now is just a half a second of data, just a tiny little segment of data from a radio telescope. So this is time going along here. And on the vertical axis, you've got radio frequency. So in this particular image we're looking at, it's a frequency of about 1.4 gigahertz. That's a 20 centimeter wavelength. That's a very common frequency for radio astronomers. And what you see there is one of these chirp signals. So this black line here. That's the signal that we're detecting, and it's only a few milliseconds wide. It's very, very brief. And you can see the higher frequencies at the top of the graph and the lower frequencies coming later at the bottom. When you add up all of these frequencies along this track, you add all of this signal together, you get this pulse here. It's what we call a de-dispersed pulse. The reason it's called that is because the radio waves are experiencing a phenomenon known as dispersion, and that's shown in this image here. Well, we've now got a cartoon of the same thing, radio frequency versus time. What we think is happening to pretty much all sources of radio waves that we observe in this way is that they're emitted from the source at the same time. A star will give out these radio waves. We'll talk about the specifics of the star shortly. The radio waves leave the star all at the same time, but they don't travel through empty space. They're actually traveling through an almost perfect vacuum. But in that empty space, the space between us and the source, there are free electrons floating around that form a very low density plasma. And that plasma causes the higher frequency waves to travel faster than the lower frequency ones. Kind of acts as a prism, so it spreads the light, the radio light, out in terms of its wavelength or frequency. The net effect of that is that the higher frequency waves arrive first and the lower frequency waves arrive later. So they're coded here. The higher frequency ones are in blue and the lower frequency ones are in red. And so the delay that you're seeing here is actually proportional to the amount of plasma that the radio waves travel through. So by measuring the delay, you're actually getting an indirect measurement of the distance to the source. So that's a very important thing that I want you to remember, this idea of dispersion. So with that sort of primer, what we're going to do now is we're going to go and just step back a little bit and see how we got to our current state of knowledge. So I'm a radio astronomer. I've been studying the universe through its radio mission for over 30 years now. I spent a lot of my time, certainly back in the 1990s, at this observatory here. This is the Parkes Radio Telescope in New South Wales, Australia. And it's a 64-meter dish. And it's one of the most beautiful, one of my favorite places on Earth, certainly one of my favorite telescopes to observe in. You can sit in the control room here, and you're under this giant structure that's moving above you as you observe. It's you feel really connected to the universe by using this telescope. It features in the movie the dish itself, which tells the story of how this telescope brought back the images from the first moon landing. So it's a very important telescope, and it plays a role in the story tonight. Not all telescopes look like that, though. There are some telescopes that are basically just wires strewn over the fields, and that's because radio waves, they generally have really long wavelengths, and they don't really need like a perfect mirror to reflect upon. They can really land on the Earth, and then they can oscillate. They can stimulate currents even in wires that are strewn across fields like the one shown here, and that electrical current is telling us about the signal that is coming from space. So one of the early experiments that was carried out in the 1960s was using this telescope here in Cambridge, and it very famously discovered the first pulsar. And the pulsar, that's worth a lecture in itself, but to cut a long story short, the discoverer of the first pulsar, Jocelyn Bell, is shown here. And Jocelyn's discovery was that the radio sky is filled with these sources that emit very regular pulses every few seconds, and in some cases down as brief as a couple of milliseconds. But here's the first one that was discovered, and what you're looking at time along here And these dips are the pulses that are received from the star, what we now call a pulsar. And they are very regularly spaced. About every 1.1 seconds you get this pulse. What's happening is that you have a star that's rotating, and it's sending this beam of radiation past you every time it rotates, and that's when you get this pulse. A little bit like a lighthouse sends out light waves as you walk along the beach and you see this flash of the light. We're seeing here the flash of the radio waves. So Jocelyn's discovery was amazing. We'd never seen anything like it before. It turns out that these pulsars are in fact born in these supernova explosions that I was talking about earlier. Here's an optical image that you're seeing in the background. It's the so-called Crab supernova remnant. It's in the constellation of Taurus, and it was first seen by our ancestors in the year 1054 AD as a visible star in the sky for several weeks. Actually, it was so bright you could see it during the day before it faded away. When you look in that spot now, you see this expanding shell of gas, which is the remains of a star that exploded in our galaxy to form one of these pulsars. And the pulsar basically is the collapsed core of that exploded star that is now spinning very rapidly. It has an incredibly high magnetic field, and it is emitting these pulses as in the manner that I just described. So you could talk about pulsars for a whole lecture or several lectures, and I would encourage you to get speakers in to do that. But for tonight's talk, it's most important to realize that this is going back now to 1968 when this pulsar was discovered. People realized back then that this particular pulsar was emitting very bright pulses occasionally. Most of the pulses that it actually emits are quite faint, and they're buried in the noise here that you're seeing in this image. But every few minutes or so, it emits a really bright pulse that is so bright that even a smallish radio telescope could see it. And that got people thinking, well, maybe we could use these radio telescopes to detect pulses coming from well outside of the Milky Way. And so people have been looking for extragalactic pulses, as they're called, or now known as fast radio bursts. People have been looking for these for a long time. So it goes back to the 1970s. There were a number of theoretical papers discussing this basic idea that I just described. The fact that there could be sources of radio waves in the distant universe that are energetic enough to produce these pulses. And so people started looking for them. John Jelly was one of the first astronomers to look for them, unsuccessfully. Vitaly Ginzburg was a theorist who saw the potential in these sources for probing the electrons along great lines of sight in the universe. And then it goes back to, on the bottom here, there's some famous astronomers that you might recognize, and physicists Stephen Hawking and Martin Rees. Stephen Hawking famously theorized that black holes, some of them would actually explode, and that explosion could emit a radio pulse, among other things. So Sturl Finney and Joe Taylor and others looked for these pulses unsuccessfully for many years, until really the situation changed about just over 20 years ago now, when Maura McLaughlin, who's my wife, but also a faculty member here at WVU, was a student at Cornell University with her advisor, Jim Cordes, and Shami Chatterjee, a fellow graduate student, who you'll see a little bit later in this talk. So one of the things that Maura and Jim worked on was a computerized way to look for these single pulses. Prior to that, some of the analyses had been had relied on visual inspection of data, but in this case, what Maura and Jim did was they wrote a set of computer software that would search the data for these dispersed pulses. Someone's knocking at my door. Hopefully they'll go away. And what you're looking at, the result there is a graph of dispersion measure versus time. And the remember, this quantity dispersion measure is basically proportional to distance going up in this direction, and then time is running along here. What you see is this background noise of just random radio signals, these little small points, but these big points, those are really bright pulses that this computer software has found at very well determined dispersions. And so this dispersion measure, this delay that we saw in that earlier graph, is showing up here as these very well defined pulses. And so this allowed Mora and others to find individual pulses from pulsars in an entirely new way, and they found a whole population of pulsars that had been missed in the Milky Way through this technique. And so then around about 2006, Mora and I moved to WVU. Here we are in front of the Green Bank telescope with our oldest son, who's now an incoming freshman at WVU. So time flies. And as new professors in our department, we were encouraged and approached by many students who wanted to work with us on astronomy projects. And one of our first students, Ash Narkovic, who's shown here, was interested in looking at some data. So we engaged them in a study of the Magellanic Clouds and looking for pulses in the Magellanic Clouds. For those of you who don't know what the Magellanic Clouds are, those are our nearest satellite galaxies to the Milky Way. They're not visible from the northern hemisphere, unfortunately, but those of you who've had the chance to go down to the southern hemisphere will have seen them, and they look like bright fuzzy blobs in the night sky, but they are in fact relatively nearby galaxies. And one of the things that we wanted to do was to see if we could find some of these individual bright pulses from the Magellanic Clouds. So again, we used the pipeline that Mora had developed to look for these pulses. And here's a test observation. So this particular observation, you can see there's time running along here, and if you look closely, it's about 2 hours in duration. This is a very long observation of the same spot in the sky. And this is a pulsar in the large Magellanic Cloud, actually, and you can see individual pulses at the same dispersion value throughout. So this is basically just verifying that the pipeline is working. This pulsar was already known; it wasn't new to us at the time, but it was a good test that our code was working. So Ash continued to look through the data, and one day they showed me this plot. And you can see up on the right here, dispersion measure versus time. You see this very bright, highly dispersed pulse that is localized here at a value of 375 in our dispersion measure units. That means that it's very far away. Not only is it very far away, and I'll tell you more about that in a second, it's actually not quite in the direction that we were thinking it might be. Here is the small Magellanic Cloud, and these are the pulsars that were known at the time. This is a map made by one of our collaborators, Froni Crawford, who's now a professor at Franklin and Marshall in Pennsylvania. And here is a footprint of the telescope's field of view. It can actually see 13 different fields on the sky at once. And the pulse, this bright pulse here, was detected in these 3 different beams, at least three different beams, and it was kind of triangulated to somewhere in between them. But you can see that's about 2 degrees away from the center of the small Magellanic Cloud, and we're not actually looking directly at the small Magellanic Cloud itself. We're actually just looking out into the universe. So this pulse has a much larger dispersion than was expected from the small Magellanic Cloud. That's the first thing. But secondly, we're not even looking in that direction, so the implication is it's coming from much farther away. And when we calculate how much dispersion we get, or we expect from just the universe in general, it turns out that these sources can come from literally billions of light years away. And so in this particular case, we estimated the pulse to be at a distance of about 3 billion light years. And here's the picture that I have in my mind's eye when I think about this story now. As the signal that we were just looking at is generated from a significant distance away from the Earth, which is somewhere here in the Milky Way. And that pulse has traveled literally across the universe to get to us. So it's traveled 3 billion years to get to us. And the pulse has kind of been dispersed gradually over time as it's encountered denser regions where there are more electrons to do this dispersion. So it gets some dispersion from the host, it gets some dispersion from intervening galaxies and our own galaxy. And all of those contributions add up to the pulse arriving at the telescope and having this very characteristic shape. So this was our observation back in 2007, and we inferred a distance. We didn't measure it directly at that time, but we figured that at that distance, the pulse was actually 1 trillion times more luminous than anything we'd ever seen before. It's so bright that it's putting out as much energy as the sun does in only a few milliseconds. The sun puts the same amount of energy out in a month. So it seemed to be something entirely new. You can see that a little bit on this graph here when you look at the luminosity. So this is the sort of intrinsic brightness of the source, if you like, on this axis. And this axis here is basically the time scale of the source. So here are all the pulsars that were known at the time, and these are the individual pulses that Mora found. Here are some of these giant pulses from the Crab Nebula that I talked about, and there's somewhat over here. But this object here that at that point has started to be called after me, the Lorimer burst, was so bright that it's way up here on the diagram. It's like well away from anything else. So it seemed to be something entirely new. And so then, the big question is, what could it be? What sort of energetics it had? I kind of alluded to that. So it's something very bright. It also was a very short duration pulse. So the pulse width here gives you clues that the object itself must be quite small. It couldn't be just a galaxy that's thousands of light years across that's emitting a pulse only a few milliseconds in size. It must be coming from something like a compact star that has this energy compressed into a small amount of space to produce a pulse of that duration. So the sorts of things that we were thinking about, and still are thinking about, are neutron stars, pulses from neutron stars, or supernova explosions, or coalescences of compact binaries that are all part of the astronomers' box of delights that we like to study in various ways. So there were plenty of candidates for this signal, but we just didn't have enough information to say which of them it could be. So this was in 2007. The Lorimer burst itself, you can find it on Wikipedia and read a bit more about it. It's kind of crept into popular culture a little bit. You can find out about it in some books now. There's also a really great instrumental rock band that has the name Lorimer Burst, and here's the cover of their album Dispersion. So you might want to check that out later on. But it kind of that pulse kind of took on a life of its own. And our paper, excuse me, here's the abstract of the paper from 2007. And one of the big things that we predicted from that initial observation was that if the pulse that we saw was indicative of a whole population, then there must be many, many hundreds of them going off over the sky in a given day. And that's because the Parkes telescope can only see a relatively small field of view at a given time, and we hadn't looked for that long. So there were lots of predictions here that we could follow up on, and indeed people went and looked for other pulses, and some of them were found. Sarah Burke-Spolaire, who is also a faculty member here at WVU, was back then a PhD student in Australia, and started looking for these pulses in other data sets. She found some, but they turned out to be actually of not of celestial origin, but of terrestrial origin. They had similar characteristics to the original Lorimer burst, but they also showed up in all of the detectors of the Parkes telescope, which meant that they were coming from so much closer by. These signals were nicknamed peritons after a Greek, mythical Greek beast, basically an elk that casts a human shadow, a flying elk. So it's something that's masquerading as something else. And this kind of muddied the water for quite a while. We put out our first paper in 2007, and it wasn't until 2013 that clear, convincing evidence for more of these sources was found. And here's a paper showing 4 more of these, what are now dubbed fast radio bursts, in a survey that was published in 2013. So here's the dispersion that is measured for these radio signals versus galactic latitude, the angle away from the galactic plane. These red points are here. These are all pulsars in our Milky Way. And so you can see they form a very well-defined envelope, and that can be understood actually quite easily as the electrons in the Milky Way. But these are the fast radio bursts. You can see they're quite a distinct population from the pulsars. They have much more dispersion than the pulsars themselves do. And that's because they're coming from much farther away, and that additional dispersion is coming from beyond the Milky Way. So this was the bold headline of that paper, a population of fast radio bursts at cosmological distances. And that's subsequently been borne out. One thing that had to be resolved, though, that I'll just mention here quickly, is that the peritons themselves, which were finally tracked down to interference coming from microwave ovens. And here's a microwave oven being opened, and then in the control room, by that time they had sufficient processing power that they could look at the data in real time and see the pulse coming into the telescope from the microwave oven. Emily Petrov was the lead researcher in this study, and there's also an interesting graph down here that you can see where the peritons actually peak at around lunchtime in Australia, which is the time when the microwave was in prime use in the cafeteria. The rest of the fast radio bursts that are known at that time are scattered around 0 to 24 hours. So that kind of put that to rest. The rest of my talk, let me just keep an eye on the clock here. I'm going to just summarize the plethora of results that's been happening in the last 8 years or so. Beginning in 2016, at that point, no burst had ever been seen to repeat. It was thought or suspected that they might just be one-off events, although people hadn't proven that by any means. And this observation that was led by Laura Spittler and Paul Schultz in a paper in 2016 showed that there was one source at least that was repeating. And so that was a very significant discovery because it meant that the bursts couldn't be coming from an exploding type of source. More likely it was coming from something that could produce repetitive bursts. So again, something that explodes or collides would really only produce one set of bursts. Here we were seeing bursts that were spread out over months and years. So this is a recurring phenomenon, at least in this source. So that was a very interesting discovery. The other aspect of it was that the burst could actually be localized, because now we had one that was going to repeat. Astronomers could point different types of radio telescopes at that spot in the sky. Here's the Very Large Array in New Mexico that was used by Shami Chatterjee, who was pictured earlier as one of Maura's fellow graduate students. Now he's a researcher at Cornell, and in this study that he led in 2016, he used the Very Large Array to produce a very high resolution map of the sky to pinpoint the burst to this particular spot here, right, that's shown in the inset. And that turns out to actually be coincident with a galaxy. And if you zoom in closely enough, this is the galaxy where the burst is coming from, and it's unambiguous. The radio position is right on top of that galaxy. And Srihas Tendulkar was the lead author in this study that went out and measured the redshift of that galaxy. So those of you who know a bit about astronomy will know that the redshift of galaxies is basically measuring the expansion of the universe and can be used to track out the distance to distant objects where we're seeing the redshift of the light through this expansion. In this case, the redshift is measured to be 0.19, and that tracks to about 2.3 billion light years away. This was huge because it was the first time that a fast radio burst had ever been measured directly, a distance to it. This is as good as you're going to get, as good a proof as you can see that these things are cosmological in origin. So that was a really big deal. And then since then, in the past 5 years, the field has really exploded. By around 2016, 2017, there were maybe about 30 or so bursts known, something like that, by different telescopes around the world. And that was quite a good sample to begin with, but we knew that hundreds or perhaps thousands of them were going off every day, and so we needed a telescope that could see more of the sky to detect them. And one of these telescopes, really the first one to come along that really changed the game in this regard, is known as CHIME. And CHIME is the Canadian Hydrogen Intensity Mapping Experiment. You can look it up. It's in Penticton in Western Canada. And it is a set of 4 cylinders, 100 meter in length, that are are shown in this picture here. And at the axes of these cylinders are actually receivers that the radio waves are collected. And here's the CHIME team that they basically are completing the construction of this telescope. It turns out it was built for another type of astronomy experiment that it's doing and is being very successful at. But it turns out that this telescope is really good at seeing pulsars and fast radio bursts. And basically, as soon as they turned on, they started seeing 3 of them every day. That, on average, about 3 a day. And so suddenly they amassed this huge catalog of bursts. And here are the first detections that they were showing. And that's really just because the field of view of this telescope is now about 200 square degrees rather than just about around the size of the full moon, a fraction of a square degree, which is previously the state of the art. So CHIME put out its first catalog of sources of over 500 fast radio bursts a few years ago. There's now several thousand of them that are known, and we're eagerly anticipating the next catalog coming out. But already there's such a wealth of results that have come from this study. Here are some of the bursts themselves. You can see they all have like different morphological shapes. You're looking at frequency versus time. Many of them have now been identified with different galaxies. We see them in different areas of the galaxy, different types of galaxy, and also different there are some that are in globular clusters within galaxies themselves. So there's no one certain type of galaxy or environment that seems to host an FRB, and we'll come back to that later. There seems to be pretty good evidence, though, that there are multiple classes of them. And one of the things that CHIME is showing is that because it's seeing the sky every day as the Earth rotates, seeing the same patch of sky every day, so it's able to keep score of the FRBs that are repeating and the ones that so far don't. And there seems to be some differences in their appearance. I'll just focus in on this diagram down here, which is a schematic that's based on real data. But the one-off bursts tend to look like this. They occupy all of the frequency band pretty much, and they're relatively narrow. Whereas The repeating bursts, and these are fewer in nature, there's sort of a few to 10% of all sources seem to repeat. They occupy just a fraction of the observing band, and they have a more complex behavior. So that they not only do they behave differently, they look different to one another, the repeating and the one-off bursts. So that's a big deal that we're starting to uncover that. 2020 was a monumental year, and mostly in bad ways. It was a good year for FRBs in some ways, because that year was the discovery of a fast radio burst like object in the Milky Way. Prior to that, all of the bursts seemed to be coming well beyond the Milky Way. CHIME and another telescope, STARE-2, was able to discover a very, very bright burst that was tracked to what is known as a magnetar, a very highly magnetized neutron star in the Milky Way. And here are the discoveries, the detections from those papers. This was a huge result too, because it meant that not only did we have a sense of the extent of fast radio bursts across the universe, but we now had an object that we could at least link one of them to. We know for this one at least that it's coming from a magnetar, and so they have enough energy to explain some of the other events that we're seeing. Perhaps not all of them, but it gave us a big clue as to what could be producing these bursts. As I mentioned, many FRBs have been localized to host galaxies now. There's over 50 of them. I think it's close to 100 actually now that have been localized. And they come from different types of galaxies. Perhaps they seem to be seen less in the so-called red and dead galaxies that are where star formation has ceased. But as I mentioned, they're seen in different regions of the galaxies, and also in globular clusters where there is no evidence for recent star formation. So they're kind of ubiquitous is the short answer. The most distant fast radio burst so far has been clocked at a redshift of 1. So that was emitted when the universe was half of its current size. And that translates to about a distance of 8 billion light years that this burst has traveled. Here are different images of the galaxy that it was located to, that made that measurement, and here's the burst itself. It's an incredibly luminous burst. It puts out as much energy in a few milliseconds that our sun puts out in 16 years. And it implies that those types of events could be seen even further out in the universe. Because as we know, our universe is like just this amazing time machine, and the history of our universe can be traced by looking out farther and farther out from the Earth, and where you're looking farther and farther back in time. As astronomers, one of the most amazing things that they've been able to do is, through different studies, have been able to trace the history of the universe almost to the Big Bang itself, 14 billion years ago. We're starting to probe the universe in this region up here, but one of the things we're hoping to do in the coming years is to try to find more distant fast radio bursts that were produced when the universe was in a different phase to what it is now. So the future is very bright for this field. There are many telescopes that are being built and coming online. Some of them are shown here, that have really huge discovery potential. Whereas now we have like close to 100 localizations, we'll have thousands of them within the next decade. And so we'll really have this huge catalog of sources to study, and it's just an amazing field to watch and be a part of. There's one of the CHIME dishes has been replicated, and there's a smaller copy of one of them at Greenbank here in West Virginia, and it's run in as a network with the original CHIME dish to provide much better localizations of fast radio bursts, and that's being turned on and used as we speak. So lots of very exciting science going on here in West Virginia and around the world. There are many open questions to this work. We could come back to this slide during the Q&A, but there's all sorts of things that we want to study about fast radio bursts. We don't know whether they all repeat, for instance, or whether some of them are one-offs, and some of them, or there are multiple classes among the repeaters. What even produces the repeating burst is unclear. So that's a fascinating story. And there's a lot of interest in trying to detect fast radio bursts outside of the radio. So looking for optical emission, for instance, or X-ray and gamma ray emission, or even emission from gravitational waves. So all of those opportunities are going to be coming along in the coming years. So there's a lot to do. For those of you who are interested in this field, there are many things to get into. I'd just like to thank my collaborators, Maura McLaughlin and Matthew Bales, Fernie Crawford and Ash Narkovic, who were on this initial study. We've been fortunate to work with many students and colleagues and postdocs all around the world. We get a lot of support for our research from the foundations and federal organizations listed here. And I want to just also point out that much of the work that we do, not only here in astronomy, but as in science in general, is due to the taxpayer dollars that come through federal organizations each year, and state and federal funding that comes to support this work. And so to the taxpayers, thank you for supporting this work. What we do is somewhat abstract, but we're attracting students into science, and many of our graduates go out and have very successful careers in a variety of disciplines. And so we view what we do, as important not only for understanding the universe, but for just training the workforce here in West Virginia. So that seems like a good point for me to stop. Thank you very much for inviting me, and I look forward to hearing what questions you have.
Thank you very much, Lorimer. That was absolutely wonderful. While you were speaking, we actually had a comment come in from Jaden Miller. So interesting. So we will take this time for the next 12 minutes to do a brief Q&A period. If any of our listeners have any questions, you can go ahead and enter them into the live chat, and then Dr. Lorimer will happily answer. So first question from Wallace Payne, our MUAC Vice President. What is your favorite aspect of FRBs?
That's an interesting question. Personally, as an astronomer, I am very interested in populations of astronomical objects. And so FRBs are very interesting to me from that perspective. One of the things that I do with my students here is we develop models of the population. So in the computer, we simulate universes of fast radio bursts with different properties, and we go out and simulate those. We simulate those properties, but we simulate the detection of them with telescopes, and we try to match that with the observations that we see. So that's one of the things that I like to do on the sort of theory side, but I also just love observing. I always go back to my roots, which is just taking data with these large dishes. We're very excited. We're observing right now, for instance, with the Green Bank telescope. We have an experiment that we're observing fast radio bursts all the time. We're just looking for them all the time. We found one just a few days ago, which was great. So there's always something new going on.
So, Dr. Lorimer, while we're waiting for more questions to come in, I guess this would be an appropriate time for myself as well as Dr. McBride to offer any questions that we have for you. So you touched a bit on the origins of fast radio burst, and I'm just going to repeat basically my understanding of what you said briefly, and then you can confirm the validity of what I've understood from your talk. So basically, there have been theories that fast radio bursts have origins from core collapse supernova or massive stars shedding outer envelopes of hydrogen and helium. Is that correct? So can you assess the validity of that once more?
Yeah, so the core collapse supernova is the supernova explosion itself has enough energy that it could release in the form of an electromagnetic pulse. That's a possibility. There is not so much that is coming away. There's not enough energy that's coming in the way of the shedded outer layers of the star. What's probably most likely for however many types of sources we've got is that they're connected with this particular type of star called neutron stars, which are formed in the core collapse supernova. Those are very stable objects. They're around for billions of years. They have a vast energy supply, and if things interact with them, then they can produce pulses. And so those are the kind of astronomers go to when they start to think about models for the nature of fast radio bursts.
It's absolutely fascinating. I also had an additional question about your slide in regards to the most distant FRB so far. So could you touch a bit more on the methods that were used to discover that FRB?
Yeah, it's a really interesting question. So over time, in the last 17 years, literally, the technology has advanced such that we're no longer just using single dishes for this work. In fact, most of this work is being done by what we call arrays of telescopes. So multiple dishes that are being used collectively to synthesize a much bigger dish. And as astronomers and physicists, you're probably familiar with the idea of a larger aperture has a better resolution. And so it's able to pinpoint objects better on the sky. These radio telescopes that I started out with, the Parkes one, for instance, it can't really localize objects to better than the size of the full moon on the sky. It can do a little bit better than that, but it's not great, and you can't say, I found a pulsar with this telescope, it came from that galaxy. In order to do that, to get that result that you saw, we have to use an array of telescopes that forms this larger aperture that can then pinpoint it to a much smaller region of the sky. You then have optical astronomer colleagues that go and take pictures of that part of the sky, and they say, aha, there's only this galaxy at that position. And then you go and analyze the optical light and measure its redshift, and that's where you get the distance from it. So it's a technological breakthrough that they're able to do that. So they didn't have to wait for the source to repeat. They just collected the data with this array, formed the image, and then hours to days later they were already observing it with an optical telescope. It's a very impressive feat, which requires a large team of people to do.
Yeah, it sounds incredible. We have a new comment that just rolled in. So, Dr. Lorimer, what type of telescope would you recommend for someone who is just interested in starting out with astronomy?
Honestly, I think one of your best investments could be a really good set of binoculars. They're very portable, and here in West Virginia, you can get, you just have to get a few miles away from the city, and the skies start to get really dark, and you can, once your eyes adjust, you can pull out the binoculars and start to see, some interesting objects just with those. And so that would be my first step. If you've already done that, then you'd probably be wanting some larger aperture. They have these telescopes called Dobsonians. They look old-fashioned. They're these big cylinders that tilt around, but they're very portable and very easy to use, and actually, significantly better than binoculars for a reasonable price point. So a Dobsonian telescope would be my recommendation. Yeah.
Absolutely. Well, MUAC actually has one in our possession. So, an additional comment that we just got was, what potential do FRBs have in application? How can we use them for other astronomical studies and research?
Great question. And I didn't really have time to get into it. So let me briefly add a little bit. So we might never know fully what FRBs are. We might never truly understand the origin of them. But that doesn't stop us from using them as tools to understand other things about the universe. So what we do understand very well is this dispersion effect that I showed you right at the beginning. The physical principles for that are very well understood. It's very easy to measure, and basically each of those measurements gives you basically a count of the number of electrons along the line of sight. It's proportional to that number. And so knowing how many electrons there are out to a certain distance allows you to do kind of a census of the matter between galaxies in the universe. It allows you to weigh that part of the universe in an entirely new way. No pun intended. So you're looking at the matter between the galaxies in a way that is really complementary to other parts of astronomy. And so you're really studying what's known as the intergalactic medium at that point, which is very cool, and doesn't require that you understand fully the FRB. You can also look at the characteristics of the radio waves in a little bit more detail and look at their polarization properties. Look at the orientation of the electromagnetic wave, and from that orientation you can actually infer what sort of magnetic field there is along the line of sight. So not only can you weigh the universe, you can study the magnetism of the universe on large scales, which again is quite unique. People are starting to use FRBs now because they start to understand, as they understand what's known as the cosmic web, the space between galaxies. As they start to understand that more, the hope is that they can use FRBs to measure Hubble's constant in a new way, so to actually measure the expansion of the universe. So you really become, with a huge community of astronomers, you really become only limited by your imagination. There are new and creative ways being produced all the time, and so as our measurements get better, there'll be more and more little ways to look at the large-scale structure of the universe through these objects.
Dr. McBride, do you have any questions?
So I guess one question would be is for an incoming undergraduate student, what sort of knowledge would they have to have in order to be able to sort of start pursuing this research specifically? What levels of maybe math and physics to sort of give students an idea of the track to sort of follow?
Yeah, it doesn't require a lot of prior knowledge, and we actually engage students in high school and in middle school in some cases in this type of research. At the very simplest sort of entry level, we have students just looking at data from the telescope. It's kind of given to them, and we explain what the axes mean and what to look for. And our eyes are just very good at looking for patterns once we're told what they are. And so many people get their start by just looking through hundreds of these plots. And but obviously that gets a bit tiring after a while, and there are actually more automated ways to do that. But it generates interest. And then what I would say is the students, we work with a lot of undergraduate students, but as many freshmen come in wanting to, they've learned a bit of programming, they've taken mechanics class, perhaps they've done a little intro E&M class, and so at that point they're really ready to do one of these simulations of FRBs, and or perhaps write some data analysis code. But the coding skills, I think, are quite important. So if you're, listening to this and thinking about what I might need to develop, I would go and brush up on your Python or learn some Python. That would be a really strong recommendation if that's not something you've done already.
Fantastic. Thank you.
So I currently don't see any more comments coming in through our live chat at the moment. But Dr. Lorimer, this has been an absolutely wonderful experience getting to hear you talk about fast radio burst. And we really do thank you for being our first speaker in this series. It's been an absolute honor. And it makes us more excited for, the episodes within the series in the future and what we can continue to accomplish with it. So again, thank you.
Oh, you're very welcome. Thank you for having me, and good luck with the rest of the series. I'll be watching.
Thank you. Thanks again. I appreciate it, and so does everybody else.
Thank you. Have a good evening.
You too.
You too.